From the time of Thales of Miletus in the 5th century BC down to that of Copernicus in the 15th and Tycho Brahe in the 16th century AD, observations have been from time to time carried on with more or less correctness, until in the present day the altitudes of the lunar mountains have been determined with exactitude. Galileo explained the phenomena of the lunar light produced during certain of her phases by the existence of mountains, to which he assigned a mean altitude of 27,000 feet. After him, Hevelius, an astronomer of Danzig, reduced the highest elevations to 15,000 feet, but the calculations of Riccioli brought them up again to 21,000 feet. At the close of the 18th century, Herschel, armed with a powerful telescope, considerably reduced the preceding measurements. He assigned a height of 11,400 feet to the maximum elevations and reduced the mean of the different altitudes to little more than 2,400 feet. But Herschel's calculations were in their turn corrected by the observations of Halley, Nasmyth, Bianchini, Gruithuisen, and others, but it was reserved for the labors of Boer and Meidler finally to solve the question. They succeeded in measuring 1905 different elevations, of which 6 xc 0 feet and 22 xc 400 feet. The highest summit of all towers to a height of 22,606 feet above the surface of the lunar disk. At the same period, the examination of the moon was completed. She appeared completely riddled with craters, and her essentially volcanic character was apparent at each observation. By the absence of refraction in the rays of the planets occulted by her, we conclude that she is absolutely devoid of an atmosphere. The absence of air entails the absence of water. It became, therefore, manifest that the Selenites, to support life under such conditions, must possess a special organization of their own, must differ remarkably from the inhabitants of the earth. At length, thanks to modern art, instruments of still higher perfection searched the moon without intermission, not leaving a single point of her surface unexplored. And notwithstanding that her diameter measures 2150 miles, her surface equals the 1/15th part of that of our globe, and her bulk the 1/49th part of that of the terrestrial spheroid. Not one of her secrets was able to escape the eyes of the astronomers, and these skillful men of science carried to an even greater degree their prodigious observations. Thus they remarked that, during full moon, the disk appeared scored in certain parts with white lines, and during the phases with black. On prosecuting the study of these with still greater precision, they succeeded in obtaining an exact account of the nature of these lines. They were long and narrow furrows sunk between parallel ridges, bordering generally upon the edges of the craters. Their length varied between 10 miles, and their width was about 1,600 yards. Astronomers called them chasms, but they could not get any further. Whether these chasms were the dried-up beds of ancient rivers or not, they were unable thoroughly to ascertain. The Americans, among others, hoped one day or other to determine this geological question. They also undertook to examine the true nature of that system of parallel ramparts discovered on the moon's surface by Gruithuisen, a learned professor of Munich, who considered them to be a system of fortifications thrown up by the Selenitic engineers. These 2 points, yet obscure, as well as others, no doubt, could not be definitely settled except by direct communication with the moon. Regarding the degree of intensity of its light, there was nothing more to learn on this point. It was known that it is 300,000 times weaker than that of the sun, and that its heat has no appreciable effect upon the thermometer. As to the phenomenon known as the ashy light, it is explained naturally by the effect of the transmission of the solar rays from the Earth to the moon, which give the appearance of completeness to the lunar disk, while it presents itself under the crescent form during its first and last phases. Such was the state of knowledge acquired regarding the Earth's satellite, which the Gun Club undertook to perfect in all its aspects, cosmographic, geological, political, and moral. Chapter 6. Permissive limits of ignorance and belief in the United States. The immediate result of Barbicane's proposition was to place upon the orders of the day all the astronomical facts relative to the Queen of the Night. Everybody set to work to study assiduously. One would have thought that the moon had just appeared for the first time, and that no one had ever before caught a glimpse of her in the heavens. The papers revived all the old anecdotes in which the son of the wolves played a part. They recalled the influences which the ignorance of past ages ascribed to her. In short, all America was seized with selenomania or had become moon-mad. The scientific journals, for their part, dealt more especially with the questions which touched upon the enterprise of the Gun Club. The letter of the Observatory of Cambridge was published by them and commented upon with unreserved approval. Until that time, most people had been ignorant of the mode in which the distance which separates the moon from the earth is calculated. They took advantage of this fact to explain to them that this distance was obtained by measuring the parallax of the moon. The term parallax proving caviar to the general, they further explained that it meant the angle formed by the inclination of two straight lines drawn from either extremity of the Earth's radius to the moon. On doubts being expressed as to the correctness of this method, they immediately proved that not only was the mean distance 234,347 miles, but that astronomers could not possibly be in error in their estimate by more than 70 miles either way. To those who were not familiar with the motions of the moon, they demonstrated that she possesses two distinct motions, the first being that of rotation upon her axis, the second being that of revolution round the Earth, accomplishing both together in an equal period of time, that is to say, in 27 1/3 days. The motion of rotation is that which produces day and night on the surface of the moon, save that there is only one day and one night in the lunar month, each lasting 354 1/3 hours. But happily for her, the face turned toward the terrestrial globe is illuminated by it with an intensity equal to that of 14 moons. As to the other face, always invisible to us, it has of necessity 354 hours of absolute night, tempered only by that pale glimmer which falls upon it from the stars. Some well-intentioned, but rather obstinate persons could not at first comprehend how, if the moon displays invariably the same face to the earth during her revolution, she can describe one turn round herself. To such they answered, "Go into your dining room and walk round the table in such a way as to always keep your face turned toward the center. By the time you will have achieved one complete round, you will have completed one turn around yourself, since your eye will have traversed successively every point of the room. Well then, the room is the heavens, the table is the earth, and the moon is yourself." And they would go away delighted. So then the moon displays invariably the same face to the earth. Nevertheless, to be quite exact, it is necessary to add that, in consequence of certain fluctuations of north and south, and of west and east, termed her libration, she permits rather more than half, that is to say, 5/7, to be seen. As soon as the ignoramuses came to understand as much as the director of the observatory himself knew, they began to worry themselves regarding her revolution round the earth, whereupon 20 scientific reviews immediately came to the rescue. They pointed out to them that the firmament, with its infinitude of stars, may be considered as one vast dial plate, upon which the moon travels, indicating the true time to all the inhabitants of the earth. That it is during this movement that the Queen of Night exhibits her different phases, that the moon is full when she is in opposition with the sun, that is when the three bodies are on the same straight line, the earth occupying the center, that she is new when she is in conjunction with the sun, that is, when she is between it and the earth, and lastly that she is in her first or last quarter, when she makes with the sun and the earth an angle of which she herself occupies the apex. Regarding the altitude which the moon attains above the horizon, the letter of the Cambridge Observatory had said all that was to be said in this respect. Everyone knew that this altitude varies according to the latitude of the observer. But the only zones of the globe in which the moon passes the zenith, that is, the point directly over the head of the spectator, are of necessity comprised between the 28th parallels and the equator. Hence the importance of the advice to try the experiment upon some point of that part of the globe, in order that the projectile might be discharged perpendicularly, and so the soonest escape the action of gravitation. This was an essential condition to the success of the enterprise and continued actively to engage the public attention. Regarding the path described by the Moon in her revolution round the Earth, the Cambridge Observatory had demonstrated that this path is a re-entering curve, not a perfect circle, but an ellipse, of which the Earth occupies one of the foci. It was also well understood that it is farthest removed from the Earth during its apogee and approaches most nearly to it at its perigee. Such was then the extent of knowledge possessed by every American on the subject, and of which no one could decently profess ignorance. Still, while these principles were being rapidly disseminated, many errors and illusory fears proved less easy to eradicate. For instance, some worthy persons maintained that the Moon was an ancient comet which, in describing its elongated orbit round the Sun, happened to pass near the Earth and became confined within her circle of attraction. These drawing-room astronomers professed to explain the charred aspect of the Moon, a disaster which they attributed to the intensity of the solar heat. Only, on being reminded that comets have an atmosphere, and that the Moon has little or none, they were fairly at a loss for a reply. Others again, belonging to the doubting class, expressed certain fears as to the position of the Moon. They had heard it said that, according to observations made in the time of the caliphs, her revolution had become accelerated in a certain degree. Hence they concluded, logically enough, that an acceleration of motion ought to be accompanied by a corresponding diminution in the distance separating the two bodies, and that, supposing the double effect to be continued to infinity, the Moon would end by one day falling into the Earth. However, they became reassured as to the fate of future generations on being apprised that, according to the calculations of Laplace, this acceleration of motion is confined within very restricted limits, and that a proportional diminution of speed will be certain to succeed it. So then, the stability of the solar system would not be deranged in ages to come. There remains but the third class, the superstitious. These worthies were not content merely to rest in ignorance. They must know all about things which had no existence whatever, and as to the Moon, they had long known all about her. One set regarded her disk as a polished mirror, by means of which people could see each other from different points of the Earth and interchange their thoughts. Another set pretended that out of 1,000 new moons that had been observed, 950 had been attended with remarkable disturbances, such as cataclysms, revolutions, earthquakes, the deluge, etc. Then they believed in some mysterious influence exercised by her over human destinies, that every Selenite was attached to some inhabitant of the Earth by a tie of sympathy. They maintained that the entire vital system is subject to her control, etc. But in time, the majority renounced these vulgar errors and espoused the true side of the question. As for the Yankees, they had no other ambition than to take possession of this new continent of the sky and to plant upon the summit of its highest elevation the star-spangled banner of the United States of America. Chapter 7. The Hymn of the Cannonball. The Observatory of Cambridge, in its memorable letter, had treated the question from a purely astronomical point of view. The mechanical part still remained. President Barbicane had, without loss of time, nominated a working committee of the Gun Club. The duty of this committee was to resolve the three grand questions of the cannon, the projectile, and the powder. It was composed of 4 members of great technical knowledge: Barbicane, with a casting vote in case of equality, General Morgan, Major Elphinstone, and J.T. Maston, to whom were confided the functions of secretary. On the 8th of October, the committee met at the house of President Barbicane, 3 Republican Street. The meeting was opened by the president himself. "Gentlemen," said he, "we have to resolve one of the most important problems in the whole of the noble science of gunnery. It might appear, perhaps, the most logical course to devote our first meeting to the discussion of the engine to be employed. Nevertheless, after mature consideration, it has appeared to me that the question of the projectile must take precedence of that of the cannon, and that the dimensions of the latter must necessarily depend on those of the former." "Suffer me to say a word," here broke in J.T. Maston. "Permission having been granted, gentlemen," said he with an inspired accent, Our president is right in placing the question of the projectile above all others. The ball we are about to discharge at the moon is our ambassador to her, and I wish to consider it from a moral point of view. The cannonball, gentlemen, to my mind, is the most magnificent manifestation of human power. If Providence has created the stars and the planets, man has called the cannonball into existence. Let Providence claim the swiftness of electricity and of light, of the stars, the comets, and the planets, of wind and sound. We claim to have invented the swiftness of the cannonball, 100 times superior to that of the swiftest horses or railway train. How glorious will be the moment when, infinitely exceeding all hitherto attained velocities, we shall launch our new projectile with the rapidity of 7 miles a second. Shall it not, gentlemen, shall it not be received up there with the honors due to a terrestrial ambassador? Overcome with emotion, the orator sat down and applied himself to a huge plate of sandwiches before him. "And now," said Barbicane, "let us quit the domain of poetry and come direct to the question." "By all means," replied the members, each with his mouth full of sandwich. "The problem before us," continued the president, "is how to communicate to a projectile a velocity of 12,000 yards per second. Let us at present examine the velocities hitherto attained. General Morgan will be able to enlighten us on this point." "And the more easily," replied the general, "that during the war I was a member of the Committee of Experiments. I may say, then, that the 100-pounder Dahlgrens, which carried a distance of 5,000 yards, impressed upon their projectile an initial velocity of 500 yards a second. The Rodman Columbiad threw a shot weighing half a ton a distance of 6 miles, with a velocity of 800 yards per second, a result which Armstrong and Palliser have never obtained in England." "This," replied Barbicane, "is, I believe, the maximum velocity ever attained." "It is so," replied the general. "Ah," groaned J.T. Maston, "if my mortar had not burst." "Yes," quietly replied Barbicane, "but it did burst. We must take, then, for our starting point, this velocity of 800 yards. We must increase it 20-fold. Now, reserving for another discussion the means of producing this velocity, I will call your attention to the dimensions which it will be proper to assign to the shot. You understand that we have nothing to do here with projectiles weighing at most but half a ton." "Why not?" demanded the major. "Because the shot," quickly replied J.T. Maston, "must be big enough to attract the attention of the inhabitants of the moon, if there are any." "Yes," replied Barbicane, "and for another reason more important still." "What mean you?" asked the major. "I mean that it is not enough to discharge a projectile and then take no further notice of it. We must follow it throughout its course, up to the moment when it shall reach its goal." "What?" shouted the general and the major in great surprise. "Undoubtedly," replied Barbicane composedly, "or our experiment would produce no result." "But then," replied the major, "you will have to give this projectile enormous dimensions." "No, be so good as to listen. You know that optical instruments have acquired great perfection. With certain instruments, we have succeeded in obtaining enlargements of 6,000 times and reducing the moon to within 40 miles distance. Now, at this distance, any object 60 feet square would be perfectly visible. If then the penetrative power of telescopes has not been further increased, it is because that power detracts from their light, and the moon, which is but a reflecting mirror, does not give back sufficient light to enable us to perceive objects of lesser magnitude." "Well then, what do you propose to do?" asked the general. "Would you give your projectile a diameter of 60 feet? "Not so." "Do you intend, then, to increase the luminous power of the moon?" "Exactly so. If I can succeed in diminishing the density of the atmosphere through which the moon's light has to travel, I shall have rendered her light more intense. To effect that object it will be enough to establish a telescope on some elevated mountain. That is what we will do." "I give it up," answered the major. "You have such a way of simplifying things, and what enlargement do you expect to obtain in this way?" "One of 48,000 times, which should bring the moon within an apparent distance of 5 miles. and in order to be visible, objects need not have a diameter of more than 9 feet. So then, cried J.T. Maston, our projectile need not be more than 9 feet in diameter. Let me observe, however, interrupted Major Elphinstone, this will involve a weight such as— My dear Major, replied Barbicane, before discussing its weight, permit me to enumerate some of the marvels which our ancestors have achieved in this respect. I don't mean to pretend that the science of gunnery has not advanced, but it is as well to bear in mind that during the Middle Ages they obtained results more surprising, I will venture to say, than ours. For instance, during the siege of Constantinople by Mahomet Roman II, in 1453, stone shot of 1,900 pounds weight were employed. At Malta, in the time of the Knights, there was a gun of the fortress of St. Elmo which threw a projectile weighing 2,500 pounds. And now what is the extent of what we have seen ourselves? Armstrong guns discharging shot of 500 pounds, and the Rodman guns projectiles of half a ton. It seems, then, that if projectiles have gained in range, they have lost far more in weight. Now, if we turn our efforts in that direction, we ought to arrive, with the progress on science, at 10 times the weight of the shot of Mahomet Roman II and the Knights of Malta. Clearly, replied the Major, but what metal do you calculate upon employing? Simply cast iron, said General Morgan. But, interrupted the Major, since the weight of a shot is proportionate to its volume, an iron ball of 9 feet in diameter would be of tremendous weight. Yes, if it were solid, not if it were hollow. Hollow, then it would be a shell. Yes, a shell, replied Barbicane, decidedly it must be. A solid shot of 108 inches would weigh more than 200,000 pounds, a weight evidently far too great. Still, as we must reserve a certain stability for our projectile, I propose to give it a weight of 20,000 pounds. What then will be the thickness of the sides? Asked the Major. If we follow the usual proportion, replied Morgan, a diameter of 108 inches would require sides of 2 feet thickness, or less. That would be too much, replied Barbicane, for you will observe that the question is not that of a shot intended to pierce an iron plate. It will suffice to give its sides strong enough to resist the pressure of the gas. The problem, therefore, is this: what thickness ought a cast-iron shell to have in order not to weight more than 20,000 pounds? Our clever secretary will soon enlighten us upon this point. Nothing easier, replied the worthy secretary of the committee, and rapidly tracing a few algebraical formulae upon paper, among which N2 and X2 frequently appeared, he presently said, "The sides will require a thickness of less than 2 inches. Will that be enough? Asked the Major doubtfully. Clearly not, replied the President. What is to be done then? Said Elphinstone with a puzzled air. Employ another metal instead of iron. Copper, said Morgan. No, that would be too heavy. I have better than that to offer. What then? Asked the Major. Aluminum, replied Barbicane. Aluminum, cried his 3 colleagues in chorus. Unquestionably, my friends, this valuable metal possesses the whiteness of silver, the indestructibility of gold, the tenacity of iron, the fusibility of copper, the lightness of glass. It is easily wrought, is very widely distributed, forming the base of most of the rocks, is 3 times lighter than iron, and seems to have been created for the express purpose of furnishing us with the material for our projectile. But, my dear President, said the Major, is not the cost price of aluminum extremely high? It was so at its first discovery, but it has fallen now to $9 a pound. But still $9 a pound, replied the Major, who was not willing readily to give in. Even that is an enormous price. Undoubtedly, my dear Major, but not beyond our reach. What will the projectile weigh then? Asked Morgan. Here is the result of my calculations, replied Barbicane. A shot of 108 inches in diameter and 12 inches in thickness would weigh, in cast iron, 67,440 pounds. Cast in aluminum, its weight will be reduced to 19,250 pounds. Capital, cried the Major, But do you know that, at $9 a pound, this projectile will cost $173,050, $173,050. I know it quite well, but fear not, my friends, the money will not be wanting for our enterprise. I will answer for it. Now what say you to aluminum, gentlemen? Adopted, replied the 3 members of the committee. So ended the first meeting. The question of the projectile was definitely settled. Chapter 8. History of the Cannon. The resolutions passed at the last meeting produced a great effect out of doors. Timid people took fright at the idea of a shot weighing 20,000 pounds being launched into space. They asked what cannon could ever transmit a sufficient velocity to such a mighty mass. The minutes of the second meeting were destined triumphantly to answer such questions. The following evening, the discussion was renewed. My dear colleagues, said Barbicane without further preamble, the subject now before us is the construction of the engine, its length, its composition, and its weight. It is probable that we shall end by giving it gigantic dimensions, but however great may be the difficulties in the way, our mechanical genius will readily surmount them. Be good enough, then, to give me your attention, and do not hesitate to make objections at the close. I have no fear of them. The problem before us is how to communicate an initial force of 12,000 yards per second to a shell of 108 inches in diameter, weighing 20,000 pounds. Now, when a projectile is launched into space, what happens to it? It is acted upon by 3 independent forces: the resistance of the air, the attraction of the earth, and the force of impulsion with which it is endowed. Let us examine these 3 forces. The resistance of the air is of little importance. The atmosphere of the Earth does not exceed 40 miles. Now, with the given rapidity, the projectile will have traversed this in 5 seconds, and the period is too brief for the resistance of the medium to be regarded otherwise than as insignificant. Proceeding, then, to the attraction of the Earth, that is, the weight of the shell, we know that this weight will diminish in the inverse ratio of the square of the distance. When a body left to itself falls to the surface of the Earth, it falls 5 feet in the first second, and if the same body were removed 542 miles further off, in other words, to the distance of the Moon, its fall would be reduced to about half a line in the first second. That is almost equivalent to a state of perfect rest. Our business, then, is to overcome progressively this action of gravitation. The mode of accomplishing that is by the force of impulsion. There's the difficulty, broke in the Major. True, replied the President, but we will overcome that, for the force of impulsion will depend on the length of the engine and the powder employed, the latter being limited only by the resisting power of the former. Our business, then, today, is with the dimensions of the cannon. Now up to the present time, said Barbicane, our longest guns have not exceeded 25 feet in length. We shall therefore astonish the world by the dimensions we shall be obliged to adopt. It must evidently be, then, a gun of great range, since the length of the piece will increase the detention of the gas accumulated behind the projectile, but there is no advantage in passing certain limits. Quite so, said the Major. What is the rule in such a case? Ordinarily, the length of a gun is 20 to 25 times the diameter of the shot, and its weight 235 to 240 times that of the shot. That is not enough, cried J.T. Maston impetuously. I agree with you, my good friend, and in fact, following this proportion for a projectile 9 feet in diameter, weighing 30,000 pounds, the gun would only have a length of 225 feet and a weight of 7,200,000 pounds. Ridiculous, rejoined Maston, as well take a pistol. I think so too, replied Barbicane. That is why I propose to quadruple that length and to construct a gun of 900 feet. The General and the Major offered some objections. Nevertheless, the proposition, actively supported by the Secretary, was definitely adopted. But, said Elphinstone, what thickness must we give it? A thickness of 6 feet, replied Barbicane. You surely don't think of mounting a mass like that upon a carriage? Asked the Major. It would be a superb idea, though, said Maston. But impracticable, replied Barbicane. "No, I think of sinking this engine in the earth alone, binding it with hoops of wrought iron, and finally surrounding it with a thick mass of masonry of stone and cement. The piece once cast, it must be bored with great precision, so as to preclude any possible windage. So there will be no loss whatever of gas, and all the expansive force of the powder will be employed in the propulsion." "One simple question," said Elphinstone. "Is our gun to be rifled?" "No, certainly not," replied Barbicane. "We require an enormous initial velocity, and you are well aware that a shot quits a rifled gun less rapidly than it does a smoothbore." "True," rejoined the Major. The committee here adjourned for a few minutes to tea and sandwiches. On the discussion being renewed, "Gentlemen," said Barbicane, "we must now take into consideration the metal to be employed. Our cannon must be possessed of great tenacity, great hardness, be infusible by heat, indissoluble, and inoxidable by the corrosive action of acids." "There is no doubt about that," replied the Major, "and as we shall have to employ an immense quantity of metal, we shall not be at a loss for choice." "Well then," said Morgan, "I propose the best alloy hitherto known, which consists of 100 parts of copper, 12 of tin, and 6 of brass." "I admit," replied the President, "that this composition has yielded excellent results, but in the present case it would be too expensive and very difficult to work. I think, then, that we ought to adopt a material excellent in its way and of low price, such as cast iron. What is your advice, Major?" "I quite agree with you," replied Elphinstone. "In fact," continued Barbicane, "cast iron costs 10 times less than bronze. It is easy to cast. It runs readily from the molds of sand. It is easy of manipulation. It is at once economical of money and of time. In addition, it is excellent as a material, and I well remember that during the war, at the siege of Atlanta, some iron guns fired 1,000 rounds at intervals of 20 minutes without injury." "Cast iron is very brittle, though," replied Morgan. "Yes, but it possesses great resistance. I will now ask our worthy secretary to calculate the weight of a cast iron gun with a bore of 9 feet and a thickness of 6 feet of metal." "In a moment," replied Maston. Then, dashing off some algebraical formulae with marvelous facility, in a minute or two he declared the following result. "The cannon will weigh 68,040 tons, and at 2 cents a pound it will cost $2,510,701. Maston, the Major, and the General regarded Barbicane with uneasy looks. "Well, gentlemen," replied the President, "I repeat what I said yesterday. Make yourselves easy, the millions will not be wanting." With this assurance of their President, the committee separated, after having fixed their third meeting for the following evening. Chapter 9. The question of the powders. There remained for consideration merely the question of powders. The public awaited with interest its final decision. The size of the projectile, the length of the cannon being settled, what would be the quantity of powder necessary to produce impulsion? It is generally asserted that gunpowder was invented in the 14th century by the monk Schwartz, who paid for his grand discovery with his life. It is, however, pretty well proved that this story ought to be ranked among the legends of the Middle Ages. Gunpowder was not invented by anyone. It was the lineal successor of the Greek fire, which, like itself, was composed of sulfur and saltpeter. Few persons are acquainted with the mechanical power of gunpowder. Now this is precisely what is necessary to be understood in order to comprehend the importance of the question submitted to the committee. A liter of gunpowder weighs about 2 pounds. During combustion, it produces 400 liters of gas. This gas, on being liberated and acted upon by temperature raised to 2400 degrees, occupies a space of 4,000 liters. Consequently, the volume of powder is to the volume of gas produced by its combustion as 1 to 4,000. One may judge, therefore, of the tremendous pressure on this gas when compressed within a space 4,000 times too confined. All this was, of course, well known to the members of the committee when they met on the following evening. The first speaker on this occasion was Major Elphinstone, who had been the director of the gunpowder factories during the war. "Gentlemen," said this distinguished chemist, "I begin with some figures which will serve as the basis of our calculation. The O-pounder shot required for its discharge 16 pounds of powder." "You are certain of this amount?" broke in Barbicane. "Quite certain," replied the major. "The Armstrong cannon employs only 75 pounds of powder for a projectile of 800 pounds, and the Rodman Columbiad uses only 160 pounds of powder to send its half-ton shot a distance of 6 miles. These facts cannot be called in question, for I myself raised the point during the depositions taken before the Committee of Artillery." "Quite true," said the general. "Well," replied the major, "these figures go to prove that the quantity of powder is not increased with the weight of the shot. That is to say, if a 24-pounder shot requires 16 pounds of powder. In other words, if in ordinary guns we employ a quantity of powder equal to 2/3 of the weight of the projectile, this proportion is not constant. Calculate, and you will see that in place of 333 pounds of powder, the quantity is reduced to no more than 160 pounds. "What are you aiming at?" asked the president. "If you push your theory to extremes, my dear Major," said J.T. Maston, "you will get to this, that as soon as your shot becomes sufficiently heavy, you will not require any powder at all." "Our friend Maston is always at his jokes, even in serious matters," cried the major. "But let him make his mind easy. I am going presently to propose gunpowder enough to satisfy his artillerist's propensities. I only keep to statistical facts when I say that during the war, and for the very largest guns, the weight of the powder was reduced, as the result of experience, to a 10th part of the weight of the shot." "Perfectly correct," said Morgan, "but before deciding the quantity of powder necessary to give the impulse, I think it would be as well." "We shall have to employ a large-grained powder," continued the major. "Its combustion is more rapid than that of the small." "No doubt about that," replied Morgan, "but it is very destructive and ends by enlarging the bore of the pieces." "Granted, but that which is injurious to a gun destined to perform long service is not so to our Columbiad. We shall run no danger of an explosion, and it is necessary that our powder should take fire instantaneously in order that its mechanical effect may be complete." "We must have," said Maston, "several touch holes so as to fire it at different points at the same time." "Certainly," replied Elphinstone, "but that will render the working of the piece more difficult. I return then to my large-grained powder, which removes those difficulties." In his Columbiad charges, Rodman employed a powder as large as chestnuts, made of willow charcoal, simply dried in cast-iron pans. This powder was hard and glittering, left no trace upon the hand, contained hydrogen and oxygen in large proportion, took fire instantaneously, and though very destructive, did not sensibly injure the mouthpiece. Up to this point, Barbicane had kept aloof from the discussion. He left the others to speak while he himself listened. He had evidently got an idea. He now simply said, "Well, my friends, what quantity of powder do you propose?" The three members looked at one another. 200,000 pounds, at last said Morgan. 500,000, added the major. 800,000, screamed Maston. A moment of silence followed this triple proposal. It was at last broken by the president. "Gentlemen," he quietly said, "I start from this principle that the resistance of a gun, constructed under the given conditions, is unlimited. I shall surprise our friend Maston, then, by stigmatizing his calculations as timid, and I propose to double his 800,000 pounds of powder." 1,600,000 pounds, shouted Maston, leaping from his seat. "Just so. We shall have to come then to my ideal of a cannon half a mile long, for you see 1,600,000 pounds will occupy a space of about 20,000 cubic feet, and since the contents of your cannon do not exceed 0 cubic feet, it would be half full, and the bore will not be more than long enough for the gas to communicate to the projectile sufficient impulse." "Nevertheless," said the president, I hold to that quantity of powder. Now, 1,600,000 pounds of powder will create 6 billion liters of gas. 6,000 millions, you quite understand. What is to be done then? Said the general. The thing is very simple. We must reduce this enormous quantity of powder while preserving to it its mechanical power. Good, but by what means? I am going to tell you, replied Barbicane quietly. Nothing is more easy than to reduce this mass to 1/4 of its bulk. You know that curious cellular matter which constitutes the elementary tissues of vegetable? This substance is found quite pure in many bodies, especially in cotton, which is nothing more than the down of the seeds of the cotton plant. Now cotton, combined with cold nitric acid, become transformed into a substance eminently insoluble, combustible, and explosive. It was first discovered in 1832 by Braconnot, a French chemist, who called it xylodine. In 1838, another Frenchman, Pelouse, investigated its different properties, and finally, in 1846, Schonbein, professor of chemistry at Bâle, proposed its employment for purposes of war. This powder, now called pyroxyle or fulminating cotton, is prepared with great facility by simply plunging cotton for 15 minutes in nitric acid, then washing it in water, then drying it, and it is ready for use. Nothing could be more simple, said Morgan. Moreover, pyroxyle is unaltered by moisture, a valuable property to us, inasmuch as it would take several days to charge the cannon. It ignites at 170 degrees in place of 240, and its combustion is so rapid that one may set light to it on the top of the ordinary powder, without the latter having time to ignite. Perfect, exclaimed the Major. Only it is more expensive. What matter? Cried J.T. Maston. Finally, it imparts to projectiles a velocity 4 times superior to that of gunpowder. I will even add that if we mix it with 1/8 of its own weight of nitrate of potassium, its expansive force is again considerably augmented. Will that be necessary? Asked the Major. I think not, replied Barbicane. So then, in place of 1,600,000 pounds of powder, we shall have but 400,000 pounds of fulminating cotton. And since we can, without danger, compress 500 pounds of cotton into 27 cubic feet, the whole quantity will not occupy a height of more than 180 feet within the bore of the Columbiad. In this way, the shot will have more than 700 feet of bore to traverse under a force of 6 billion liters of gas before taking its flight toward the moon. At this juncture, J.T. Maston could not repress his emotion. He flung himself into the arms of his friend with the violence of a projectile, and Barbicane would have been stove in if he had not been boom-proof. This incident terminated the third meeting of the committee. Barbicane and his bold colleagues, to whom nothing seemed impossible, had succeeded in solving the complex problems of projectile, cannon, and powder. Their plan was drawn up, and it only remained to put it into execution. A mere matter of detail, a bagatelle, said J.T. Maston. Chapter 10. One enemy, they, 25 millions of friends. The American public took a lively interest in the smallest details of the enterprise of the Gun Club. It followed day by day the discussion of the committee, the most simple preparations for the great experiment, the questions of figures which it involved, the mechanical difficulties to be resolved. In one word, the entire plan of work roused the popular excitement to the highest pitch. The purely scientific attraction was suddenly intensified by the following incident. We have seen what legions of admirers and friends Barbicane's project had rallied round its author. There was, however, one single individual alone in all the states of the Union who protested against the attempt of the Gun Club. He attacked it furiously on every opportunity, and human nature is such that Barbicane felt more keenly the opposition of that one man than he did the applause of all the others. He was well aware of the motive of this antipathy, the origin of this solitary enmity, the cause of its personality and old standing, and in what rivalry of self-love it had its rise. This persevering enemy the president of the Gun Club had never seen, Fortunate that it was so, for a meeting between the two men would certainly have been attended with serious consequences. This rival was a man of science, like Barbicane himself, of a fiery, daring, and violent disposition, a pure Yankee. His name was Captain Nicholl. He lived at Philadelphia. Most people are aware of the curious struggle which arose during the Federal War between the guns and armor of iron-plated ships. The result was the entire reconstruction of the navy of both the continents. As the one grew heavier, the other became thicker in proportion. The Merrimac, the Monitor, the Tennessee, the Weehawken discharged enormous projectiles themselves, after having been armor-clad against the projectiles of others. In fact, they did to others that which they would not they should do to them, that grand principle of immortality upon which rests the whole art of war. Now if Barbicane was a great founder of shot, Nicholl was a great forger of plates. The one cast night and day at Baltimore, the other forged day and night at Philadelphia. As soon as ever Barbicane invented a new shot, Nicholl invented a new plate. Each followed a current of ideas essentially opposed to the other. Happily for these citizens, so useful to their country, a distance of from 50 to 60 miles separated them from one another, and they had never yet met. Which of these two inventors had the advantage over the other, it was difficult to decide from the results obtained. By last accounts, however, it would seem that the armor plate would in the end have to give way to the shot. Nevertheless, there were competent judges who had their doubts on the point.